Hello everyone. In today's lecture, we will go over Chapter 2, describing data in numerical ways. So specifically, we will look at the measures of central tendency, variation, and shape. So central tendency means the statistics that show the center of the data, such as mean, median, mode, and geometric mean. Variation and shape are usually about things like quartiles, range, interquartile range, and we will also learn variance, standard deviation, coefficient of variation. Similarly, we will do the same statistics on the population, and we will also look at the 5-number summary, and using the 5-number summary, we will create box and discrete plots, and we will also see covariance and coefficient of correlation. So when we describe the data numerically for the central tendencies, we look at the mean, the median, and the mode. For variation, we look at the range, IQR, the variance, standard deviation, and coefficient of variation. So let's start with the central tendency measures, such as mean, median, and mode. The mean is easy. It's simply the arithmetic average. So you add up all the numbers and divide by the sample size. That will give you the sample mean. Now the median is the number in the middle. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 observations. So the number in the middle is this one. That one is the number in the middle, because on the left side you have 4, on the right side you have the 4. The number in the middle is the median. The mode is the highest frequency, so this number is repeated 3 times. So this is our mode. Now arithmetic mean is calculated in the same way whether you are using population or you are using sample. Now for the population, we show it with the notation mu. But still the idea is you add up all the numbers and divide by the population size. So you add up all the numbers, divide by the population size, that gives you the population mean. For the sample size, the logic is the same, but this time we show it with x bar. We add up all the numbers in the sample and divide by the sample size, small n. So here's an example for the mean. We have 5 numbers, 1, 2, 3, 4, 5. Add them all, divide by 5, that's 3. Here we still have 5 numbers, but now this time it is 1, 2, 3, 4, 10. You add up all numbers, divide by 5. Now the mean becomes 4. The mean doesn't have to be an exact number. It could be a fractional number as well. Now the median is the number in the middle. Now here obviously if you have 5 numbers, the number in the middle is this one, number 3. That is the median. Still here we also have 5 numbers. The number in the middle is still 3. So the idea is the median is not affected that much from the extreme values. So in some cases, the median observation is a better measure of central tendency. So the mean has a simple formula. It is when you rank all the data from smallest to the largest, n plus 1 over 2 location, the data on that location gives you the position of the median. That's not the median, that is the position of the median. So if you have, let's say, 9 numbers, 9 sample size, 9 plus 1, 10, divide by 2, 5. 5 is the location of the median. It is not the median, it is the location of the median. Now the mode is the most frequently observed value. There might be no modes, there might be several modes. For example, in this example, the highest frequency observation happens at this location. So number 9 is the mode. So here's an example. We have house prices where we have 5 observations. The first house is very expensive, 2 million. And we have another one that's 500,000, another one 300,000, and 100,000 and 100,000. How do we find the mean? You add up all the numbers, 3 million, divide by the sample size, which is 5, and that number is the mean. Now, for the median, it is the value in the middle. So we look at the middle data. That number is in the middle, and that will give us the median. Now, the mode is the most frequent. So, for example, here, that number 100,000 is repeated twice. That's why it is the mode. It's the most frequent observation. Now, how do we look at the shape of the distributions? Normally, we are looking for symmetric. Symmetric means the mean is the same as the median. The right side looks like the left side. That is symmetric. If it is left skewed, that means we have extreme observations on the left side. And in that case, the mean will be less than the median. If it is right skewed, we have extreme observations on the right side, and that means the median is lower than the mean. There's another thing also called geometric, but we'll skip that one. Now, percentiles and quartiles. A percentile is something that we all know from the exams. You know, we have a grading scale from 0 to 100. So if you divide the data into 100 parts, that is percentile. So if you have, let's say someone has an IQ score at the 19th percentile, means that he is better than the 90% of the population in terms of IQ score. That's how you calculate the percentile. Now, quartile is something that we also use very frequently. What we do in the quartile is we divide the data into 4 segments. Now, here the point is we have 4 segments with an equal number of values per segment, which means the whites, like how wide is the data, may be different. It doesn't have to be exactly equal. Now, what that means is 25% of the population is here. This is 25%. Another 25% is here, another 25% here, another 25% here. And something interesting is this Q2. Q2 is the same thing as the median. So Q2 is the middle data, and that's also named as the median. So how do you find the quartiles? Well, again, there are specific formulas. Let's say n is the sample size. The location of the first quartile equals Q1 equals 1/4 times n plus 1. The location of the second quartile is Q2, which is 0.5 times n plus 1. And the location of Q3 equals 0.75 times n plus 1. And these are the locations. So this is, you look at the location, and the data existing at that location will give you the quartile, Q1, Q2, and Q3. So here's an example. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 observations. So if you have 9 observations, the sample size is 9. 0.25 times 9 plus 1 equals 2.5. So the location is 2.5. Now this is 1, this is 2, this is 3. So let's look at number 2 and number 3. They are here. But we're looking for 2.5. So since we're looking for 2.5, that 2.5 is between 2 and 3. So it's the middle of this observations. 12 plus 13 over 2, that's equal to 12.5. That is the Q1. Now, 5-number summary. This is something that we will use frequently. What is the 5-number summary? Minimum, this is number 1. Q1, number 2. And median, number 3. Third quartile, number 4. And the maximum, number 5. So what do we do with those numbers? We draw something called box plot. So a box plot is something like this. And so this is an example of box plot. This is like the minimum is on the left side. And Q1 is like one end of the box. Q2 is somewhere in the box. And Q3 is the upper end of the box. And this one here is the maximum. Now, measures of variation. We have 5 different measures of variation. Range. Range is the easiest one. Maximum minus minimum. Range is maximum minus minimum. Interquartile range. It's actually easy. It's Q3 minus Q1. That is interquartile range. We have variance. That's based on a specific formula. And we have standard deviation, which is the square root of variance. And we have coefficient of variation, which is again based on a specific formula. Now IQR is the easiest one. Range is also easy. IQR, you find Q3 and you find Q1 and you take the difference. That gives you IQR. So IQR is an example of like where is the middle 50% located. So your 50% of the data is located between Q3 and Q1. Now box and discrete plot. I just mentioned that also as box plot. I think I will use just box plot. That's easier. I think box was the professor, Whisker was a student, and they developed this plot together. Or maybe it was otherwise. But it was professor student. They developed this box together. So this is an example of box plot. And let me draw this again. Now we have data. Now we don't see it here, but we have data. The minimum is 12. That is the minimum. And Q1 is 30. Q2 is 45. Q3 is 57. And the maximum is 70. That's a box plot. This is actually a horizontal box plot. But if you like shift it like this, that will be a vertical box plot. Now variance is based on this formula, and we will use this formula very frequently. Now the variance formula is slightly different from population to sample. For the population, we show the variance with sigma square. That's our population. You add up all the observations, deviations, take the square and divide by the population size. So here we divide by the population size. And that's the difference. That's why I'm highlighting it. Because for the sample, we show the variance with s square. Now again, we find the differences from the mean, take the squares, but this time we divide by n minus 1. It's called sample size adjustment. That's why we have a difference between population and sample variances. Otherwise, the logic is the same. And in any case, you take the square root of the variance. That will give you standard deviation. So basically, standard deviation for the population is sigma, and that's equal to the square root of the variance. So if you take the square root of the variance, that will give you standard deviation. And the formula is the same for the sample standard deviation. The sample standard, first you find the sample variance, which is s squared, and you take the square root. That will give you the sample standard deviation. Now here's an example from how to calculate standard deviation. The first step is to look at the data. We have 1, 2, 3, 4, 5, 6, 7, 8 observations. So our sample size is 8. Now you add up all the data, divide by the sample size, and that will give you the mean. And the mean is 16. So for each observation, 10 minus 16 square, 12 minus 16 square, 14 minus 16 square, and you keep doing that for each observation. And this is sample, and divide by n minus 1, 8 minus 1. That's 130 over 7. That will be your variance. And if you take the square root, that will give you 4.305. That is your standard deviation. So to find the standard deviation, first you need to figure out what is the sample size. Then you need to calculate the mean, and using the variance formula, calculate the variance. Take the square root of variance. That will give you standard deviation. Now you see different graphs here. They have the same mean. Actually, the mean is the same. But this one has a smaller standard deviation here. The yellow one, let's say, has a small standard deviation. And let's make the blue one has a larger standard deviation. Now we know this by looking at the graph, but if you calculate, actually you will see the difference. Because standard deviation is a measure of spread, and the blue line has a higher spread, obviously, although they have the same mean. So let's look at the standard deviations here. I will not do the calculations. I mean, you can do the calculations, but obviously, for example, this one, the data is in the center, so the values are concentrated near the mean. That means standard deviation is pretty low. Now for this one, it is a bit more spread, so standard deviation is somewhere higher. This one has like 2 corner centers, so they are very far away from the center. See the difference between the center. It is far away. Because it's far away, this one has the highest standard deviation. Now, coefficient of variation is also a measure of relative variation. So to find the coefficient of variation, first you need to find the standard deviation. And if you divide the standard deviation by the mean, that will give you CV, coefficient of variation. Here on the left side, this is the coefficient of variation formula for the population. On the right side, we have the coefficient of variation formula for the sample. So for example, we have 2 stocks here, and we have the data on their average price and standard deviation, and put the numbers here. This one has a coefficient of variation of 10%. For the other stock B, put the numbers here on CV, and this one becomes 5%. So basically, they have the same standard deviation, but because the price of stock B is high, its relative variation is less. So that means it's more stable. Stock B is more stable than stock A. Now there's something called empirical rule. Sometimes use that rule. If you have a bell-shaped data, like a curve like this, if you have a curve like this, and find the mean, the mu plus minus sigma will give you 68% of the values, approximately. That is the mu plus minus sigma. Now, if you go mu plus minus 2 sigma, that will give you 95% of the values. If you go mu plus minus 3 sigma, that will give you almost all, like 99.7% of the values in the population or the sample. This is called the empirical rule. Now, z-score is something we are going to use a lot, especially in normal distribution and later during this course. It's based on a formula. For each observation, xi, you subtract the mean, xi minus mu, divide by standard deviation. That will give you the z-score. So z-score equals x minus mu over sigma. So for example, you want to measure the z-score for IQ. And IQ is 121. Someone's IQ is 121. And the average is 100. So you find the 100 and take the difference. 121 minus 100. And standard deviation is 15. So the result is 1.4. So the z-score is 1.4. Now if the z-score is 0, that means it is center, it's in the middle. And for example, in the course, you will have some courses which will do curve grading. In the curve grading, your score will be based on what's your z-score. Now there's some example on how to measure group data for the weighted mean. For each weight, you multiply the mean for each weight, and again you divide by the total number of observations. And this is the same thing as the frequency type of data. So to find the mean for each frequency, you find the mean for each group, and you find the total values and divide by the sample size. That will give you the mean. Now, measures of relationship between variables. We have covariance and correlation coefficient. Now, first you need to calculate the covariance, and then you can find the correlation coefficient. So covariance is based on this formula. Covariance is calculated between two variables. Again, for the sample, we have a sample size adjustment. So instead of dividing by n, you divide by n minus 1. If this number is positive, that means there's a positive relationship. If it is negative, that means it is negative relationship. So if the covariance between two numbers is greater than 0, that means they are moving in the same direction. If the covariance between two numbers is less than 0, they are moving in opposite directions. If the covariance is 0, that means two variables, x and y, are independent. Now, what's important for us is the correlation coefficient. Once you find the covariance, you divide it by standard deviations of both of the variables. That will give you the correlation coefficient. Now, correlation coefficient is a number between 0 and 1. So let's write it here. By calculation, the correlation coefficient is always between +1 and -1. If it is close to -1, that means strong negative relationship. If it is close to +1, that means strong positive relationship. If it is close to 0, then there is no relationship between these two variables. And here is how we calculate, estimate the various correlation coefficient. Now there's here in the first graph there's 1-to-1 negative relationship, so R is -1. In the second graph, this relationship is strong, negative. As an example, this is -0.6. Now this one is a linear line, so there's no relationship. So correlation coefficient is 0. Here this is 1-to-1 positive relationship. Here we have weak positive relationship, and here again R is 0 in the last one. So this one is example. This is R equals 1, the first one. That one is R equals 1. This one is strong positive relationship. This one, so R equals 0.91. This one is also strong, but not as much strong as this one, so R equals 0.82. Now this one is again somewhat strong, R equals 0.74. This one is getting weaker, R is 0.48. This one is very weak, R is 0.1. Let's look at the negative ones. Almost like 0, but slightly negative, -0.1. Getting stronger, but still negative, -0.26. Here, the relationship between these two variables is getting stronger negatively, -0.6. This one has a correlation coefficient of -0.77. This one is -0.9. And obviously this one is, well, as you guess, this is -0.1. And this is a class activity. I plan to do this class activity in the recitation time or the lecture time or the office hours.